This second session of the morning is with online speakers, and it's my pleasure to give the talk to Paola Francesca Antonietti of the Milan University, and he's going to talk us to numerical models for earthquake, ground motion, and seismic risk assessment. Paola Francesca. Paola Francesca.
Okay.
Sorry.
No problem at all.
Okay. I think you are aware that you have 25 minutes maximum for the talk in order to have 5 minutes of discussion.
Yes.
Okay?
Okay. Thank you. So thank you very much for the introduction, and I would like to thank Gabriella, Cecilia, Margherita, and Michela for the kind invitation. I'm very happy to participate, and I apologize for not being able to join you in presence. So what I would like to discuss today is about some recent results we obtained in the field of try to combine numerical simulations of earthquake ground motion with the quantification of seismic risk assessment. Okay, so let me first thank all the people that are involved in this research. As you can see, this is a transdisciplinary research group, and in particular, I want to thank the colleagues from the earthquake engineering group at Politecnico di Milano, led by Professor Paolucci, and the industrial collaborations with Marco Stupazzini, that is an earthquake engineer at Munich Re, that is one of the largest reinsurance companies in the world. And most of the interesting questions that we address in this year comes from him and from his day-by-day experience in dealing with extreme events. So the motivation for which we started to have a look at the damages induced by earthquakes can somehow be summarized in this table. These are the most deadliest events in the world from 1980 to 2016. And they are ranked, unfortunately, by the number of fatalities. And if you have a look to the lines highlighted by in red, you can see that on top of the 10 deadliest events, 6 of them are due to large-scale earthquakes, so with a very high magnitude. And moreover, going back to our country, we know that Italy has a very high level of seismic vulnerability and seismic hazard, so that trying to support seismic engineers in order to better quantify the seismic risk of our country might be of interest. This is the conceptual map of the approach we have developed, and it is also somehow the topics I will address in the talk. So the idea is that we can make use of mathematics in a combined way. First, to predict through 3D physics-based numerical simulation the ground motion induced by earthquakes. Then we can cook up suitable vulnerability models to quantify the damages that this ground motion will induce on a man-made infrastructure. And if you combine these two ingredients, you can provide a comprehensive seismic risk analysis. So just a couple of words of the physics behind earthquakes. I'm sure that all of you knows about this, just to make clear the main points. So the energy is released over a long period of times within the earth. Sorry, the energy is stored within the interior of the earth for a very long period of times, and then it is suddenly released. This generates seismic waves that propagates through the earth layers and then reach Earth's surface. So an earthquake is, roughly speaking, the ground motion induced by the passage of seismic waves. So the location where the earthquake's origin is called hypocenter. Its projection, the projection of this point onto the surface of the earth, is called epicenter. What about the physics of seismic waves? So seismic waves can be decomposed into two main components. There are primary waves. These are characterized by the fact that the ground motion is induced in the direction which is the same of the direction the wave is propagating. Seismic waves are faster, so they travel faster with respect to shear waves that I'll address in a second, and they can travel through all types of materials. Then there are shear waves. Shear waves induce a ground motion in the plane that is perpendicular to the direction the wave is propagating. They travel slower than primary waves, and they can travel only through solid media. And in this graph, you can see the characteristic wave, primary and shear wave velocities as a function of the depth from the Earth's surface. And as you can see, first arrives primary waves and then shear waves. And from the point of view of damages, the most dangerous one are shear waves, because they induce a ground motion which lies in the plane perpendicular to the direction of propagation. So I first have a look to the how you can use computational mathematics to simulate earthquakes. The idea is that there are many ways on the market that you can employ to predict the ground motion induced by earthquakes. They can be basically classified in two different approaches. One possible approach is to go for empirical models. The most famous one are called ground motion prediction equations. These are very simplified 1D models that gives as output average quantities that are of interest within earthquake engineering, like the peak ground displacement, peak ground velocity, and spectral displacement. On the other hand, you can go for fully 3D physics-based models. That is the approach we have decided to employ. These are, of course, much more sophisticated differential models, but they have the advantage that you know as the output the full time histories. And of course, from these quantities, you can recover the average data for the sake of comparison. And why physics-based 3D simulation have become more and more interesting in the last years. The reason is the following. So empirical approaches like a ground motion prediction equation have to be calibrated in order to give you back reliable results. And of course, they are calibrated based on employing data. This is the picture of the data that are employed to calibrate a ground motion prediction equation at the European level. So any color is, any bullet is an earthquake that took place in the past. They are grouped according to the geographic location. In the x-axis, you see the distance from the distance from the hypocenter to the receiver. On the y-axis, you read the magnitude. So the shadowed region is the region where an event is sufficiently large and sufficiently close in such a way that it might induce huge damages. So the good news is that there are only few events that can potentially impact produce damages, which is a good news, of course. The bad news is that if you go for empirical models, you have only few data that are employed to calibrate those models exactly in the region of interest. So there's the risk that ground motion prediction equations are not calibrated in the correct way exactly in the region of interest. So the idea is that you can use 3D physics-based simulations to predict, so to generate synthetic earthquakes in such a way that you can predict in a much more reliable way possible damages. From the point of view of mathematics, so what we are interested in solving are the elastodynamics equations that can be written in this form with here our unknown is the displacement u, which is of course a function of space-time. This term usually takes into account the fact that the Earth is not a truly elastic medium, but it's a viscoelastic, and this is the simplest way to encode a viscoelastic behavior. To complete the model, of course, you have to supplement the constitutive equation between the displacement and the stress tensor, and you can go for very simple linear models to more sophisticated nonlinear or viscoelastic models. This is a wave propagation phenomenon, so boundary conditions are of course important, and in particular let me mention that the most important point is to impose suitable non-reflecting boundary conditions on the artificial boundaries that are introduced only for computational purposes, in such a way that you don't have spurious reflections and refractions on these artificial boundaries. So the approach we have decided to employ for the numerical discretizations try to answer to the main challenges that this kind of problem features. That means that are the need of high order accuracy to keep numerical distortion and dissipation error as low as possible, flexibility in the handle of the geometric constraints and heterogeneities of the material, and a natural orientation towards high order, high performance computing simulations. So for such a reason, we have decided to go for high order discontinuous Galerkin finite element methods. So this is the main approach behind our computational approaches. So we have our computational domain. We chop it in many pieces. This is usually provided by seismic engineers and takes into account the stratigraphy, the different characteristics of the soil, and different physics constraints that have to be satisfied. And we go for a conforming finite spectral element approach within each subdomain, and a discontinuous approach only between one subdomain and the neighboring one. This, according to our experience, try to balance the flexibility in the construction of the grid and in the construction of the discretization space, while limiting the proliferation of the total number of degrees of freedom that would make this kind of computations too expensive from the practical point of view. This is the formulation. It's quite standard in the DG setting. I won't enter too much in the details. The only point I want to make is that since our discrete field is going to be discontinuous, the discrete formulation has to be suitable, defined, in order to penalize, in a weak sense, the jumps of the discrete displacement and the jump of the discrete test functions. This is the semi-discrete formulation. It can be fully analyzed. That means that the scheme is stable. So the energy, and it is dissipative, but this is what one would expect. And you can provide optimal semi-discrete error estimates in a suitable energy norm. Then you go for time integration. The most popular scheme in this context is the leapfrog scheme, because with the proposed approach, the mass matrix is diagonal. So advancing in time is not very expensive, even with the explicit scheme. And moreover, the physics tells you that the phenomenon is very fast. So in any case, you might be forced to take a very small time step in order to correctly capture the propagation of the wavefronts. And I'll skip the part of verification and validation, but we have tested our scheme in either synthetic test cases where a semi-analytic exact solution is known. These are known as a SCEC benchmark programs that are very common in the seismic engineer community. And we have also validated the proposed approach on earthquakes that happen by comparing the synthetic seismogram with the data recorded during the events. And this is an example carried out from the earthquake that affected the north of Italy, so the Pianura Padana earthquake near Mirandola. Now we have a tool to predict the ground motion induced by the earthquake, and we wanted to include in our computational model suitable vulnerability models. And again, there are two approaches. The first one is based on fragility curves. This is again an empirical approach to quantify the damages of structures. This is very much indicated for regions where, so whenever you want to address the impact of an earthquake of a densely populated area, like a city. Of course, it is not the case whenever you want to address the impact of a possible earthquake on strategic buildings or on buildings that belongs to the cultural heritage of a country, because these are unique and cannot be treated as conglomerates of buildings. So in that cases, and given the topic of the workshop, I will discuss in the last 5 minutes how you can perform structural analysis whenever you want to assess possible seismic damages on strategic buildings as historical buildings. In that case, you have to include the model of the building on top of your computational model. And this is called like the structural analysis of the building. And so I try to show you the flow chart addressing a concrete example. This is a simulation of the earthquake that took place in Athens in 1999. The event had a moment magnitude 6.0. And here we are interested in investigating defects on the Parthenon. This is the computational model. So as you see, this is a truly multi-scale problem in the sense that our computational domain is roughly 30 kilometers times 45 kilometers times 39 kilometers. So this is the computational box. Then if you make a zoom, this is the Acropolis Hill, which is much smaller and is put on top. And this is a zoom of the Acropolis. These are the characteristic compressional and shear waves velocities that are calibrated from the geologist, of course, not by ourselves, and the mass densities according to the different kind of materials. And on top of that, in the model, there's the Parthenon. So the geometric feature has been reconstructed starting from the CAD file of the Parthenon, and we have constructed a mesh, and the Parthenon is included in the computational model. And let me make a comment. So the simulations and the results I will show you in a second have been obtained with frequencies that arrives for the moment up to 5 Hertz. This is a preliminary study in the sense that 5 Hertz are not enough to fully capture the response of the building. So we are now negotiating with the seismic engineers in the sense that they would like to arrive up to 100 frequencies. This is a lot from the computational viewpoint, and most important for the level of granularity on which we have information on the data, which are of course affected by uncertainty. We have been able to arrive in a quite satisfactory results up to 30 Hertz, and now we are trying to push towards high order frequencies. So this is the mesh parameters that we mount on top, the computational domain. So n is the polynomial approximation degree. Since we are using a discontinuous framework, we can balance it in such a way that we have enough points per wavelength according to the phenomenon that we are propagating and the characteristic of the soils. And the same holds for the mesh size, which is calibrated in order to make sure that we capture the physics. And this is a zoom of the region near the Acropolis and of the Acropolis itself. And this is the computational grid of the Parthenon, which of course needs a very small mesh size in order to capture all the details. These are the snapshots, 4 snapshots of the velocity magnitude computed. So you see here, this is the projected fault. This is the epicenter, and these are 4 time snapshots of the computed velocity field. And this is an animation. So you see in the background the Philly fault, which is the huge fault that is exactly beneath the city of Athens. And of course, the displacement has been magnified only for visualization purposes. And here you see the peak ground velocity. What happens to the Parthenon? Here you see a zoom of what happens, so how seismic wave propagates and impact the Parthenon. And this has been, it has 300 times exaggeration only for visualization purposes. So how this fully 3D physics-based approach compare with empirical models to quantify the impact of an earthquake as the ones I discussed before, and with the data. So this is a comparison between our simulations. So the green, orange, and blue dots are the computed peak ground velocity at three different locations with different soil properties, and these are compared with the empirical model based on ground motion prediction equations. This is the red line, and then you have the interval of confidence, and so there's an agreement of the behavior observed from the fully 3D physics-based approach with the empirical models. What about the true data? So the data that has been measured during the 99 event. So this is the computed displacement in 3 different this is the computed displacement in one station that is located near the Parthenon, and the blue line, the black line is the true data. The gray line is the simulated data, and what you see is here in the panel of on the left, you see the full time history. So in the full waveform of the displacement. And here you see the Fourier amplitude spectra. And so the results are quite in agreement. There's a lot of room for improvement. And one of the aspects is that we are still with a too low frequency in order to make sure that we capture what is happening whenever we approach to high frequency components. But given that the computational domain approach, of course, needs some simplification, we are quite satisfied of the obtained results. And so I'll skip the part where you go for empirical models, and I directly go to the conclusion for, sorry, matter of times. So what we have done is try to use computational models in a comprehensive flow chart that goes from the modeling of the earthquakes up to the quantification of vulnerability of buildings. This can be used to address both the strategic structure that need to model buildings as a standalone system within the computational models. There are also approaches that are based on empirical fragility curves that I didn't discuss, but they are more suited for densely populated area. So what we are doing, so there's a room of doing, more, of course, for improvement. We are now trying to go also to include fractures in the model, and to include and to study also flows in networks of fracture that can have a role within this context. And we try to use artificial neural networks to improve the computational efficiency of our numerical approach. And of course, there's the issue of uncertainty quantification, because here data are affected by errors, and this is, in our opinion, something that has to be taken into account. And I thank you for your attention.
Thank you. Use this one. Thank you very much for your very, very interesting talk, and for staying in the time, which was not easy with all the
Sorry, I hope I not rushed too much.
I think it was perfect. There is any question, curiosity, comments from the audience?
Curiosity, No, vediamo se prova. No.
Wait a moment.
Ciao Paola. Thank you for your talk. Two curiosity. One is that you need some adaptive methods, because you are a wave so you perform a computation. You need some adaptive methods or not. And this is for in your last slide. You mentioned artificial neural networks. Use artificial neural networks exactly for that, in order to activate the solutions. And the second one is the curiosity. Is because I don't know, it's possible how is possible to estimate what is the focus? So is a data or something you have to estimate, something from the data in order to estimate where is the focus of the world?
Sorry, Giovanni, I think I think I didn't get the last part of the question.
Okay, the last
the
part
estimate of the theoretical estimate.
It's about adaptive methods.
Yes.
Possible to do with artificial networks you see in
yes,
the last
yes.
slide. The second one is about an estimate of the focus, because I think it's a data or something to how it's possible
it
to
is a risk map.
yeah. It's possible to detect from a risk map.
Okay. Okay. So thank you for the question. So to answer to the first question, Well, adaptivity now is performed in two ways. Well, actually, is performed first a priori. So starting from the physics of the problems, we make sure that we calibrate the measure size and the polynomial approximation degree in such a way that we follow the rule of thumb of engineers. So having enough points per wavelength. The idea is to have at least 4 or 5 points for wavelengths. But then, of course, there's a lot of, so our wish is also to go for a posteriori error estimates, and in particular space-time adaptivity. But just to give you an idea, so the simulation I show you, it's 800 millions of degrees of freedom. So now the code has been fully optimized on the Cineca supercomputing cluster, and one simulation, it takes roughly 4 to 5 hours. So any adaptivity that has to be mounted on top of them should be made very, very efficient from the point of view of parallelization and the high performance computing stuff. We have some indicators for space-time adaptivity, which, but at the moment, they are not enough efficient to be included. As for the artificial, as for the use of neural networks, so we are investigating two approaches, which I didn't have time to discuss. So the first one is to incorporate hybrid gray box, in the sense to use neural network to improve the numerical scheme. So as any numerical scheme, especially in the DG setting, you have to tune parameters. This can be fed up into a machine learning approach. And then there is also another hybrid approach to use data and machine learning to try to enrich the behavior at high frequencies in order to mitigate the effect of roughness of data. So we have an iterative approach where we have the simulation, we try to go to high frequency, we use the data, and we use machine learning to construct to go to the high frequency stuff. And I forgot this question.
I think was a point about the role of this kind of simulation, which I suppose is just making risk assessment and maps and stuff of this time. Is it true?
Yes. So the idea is that so structural engineers knows, because buildings are constructed exactly with this kind of perspective, which is the maximum solicitation, which is expressed in terms in this context of spectral displacement, which is basically very linked to the displacement that the ground motion induced on the building. And given a spectral displacement, they can predict whether a given building might be subjected to a complete failure, extensive failure, and so on. To give you an idea, whenever a building is projected, the law prescribes that there's a certain solicitation, and the building has to go at most into extensive damages, but not a complete damage. This is done to preserve human lives, of course. So this is how these studies can be employed, because with synthetic scenarios, you can predict the spectral displacement. And on top of that, you can predict the damage state variable.
Thank you very much.
Thank you.
I think that we have to go quickly to the next talk. And thank you again very much. Okay, so now we have, I think, a little time that we need in order to pass to the recording. Okay, so let's go to the next talk, which is from Sorin Hermon. I hope it's right pronunciation, from the Cyprus Institute. And he is presenting a talk on 3D documentation technologies for conservation and preservation of heritage monuments, the 4CH project. Please, Professor, I ask you also to stay on the 20-25 minutes in order to have time for discussion.
Okay, so thank you very much. I hope you can hear me clearly and you can also see my screen clearly. My name is Sorin Hermon and I'm part of the consortium that works on a newly funded EU project called 4CH. The coordinator is also co-author of this talk, Francesco Tacetti from the National Institute of Nuclear Physics, together with Franco Nicolucci from Pini University of Florence and Roberto Di Giulio from Inception. This will be a presentation talking about the project itself, the aims, what we want to do. I would like to highlight from the beginning that this is not a typical EU project, but it aims to set up, it has a vision for a long-term future activity, because one of the main goals of the unit, the DG unit that came up with this call is to set up something that they are calling competence center, and I will talk about it in the next slides. The consortium itself is composed of research institutes from various countries, universities, public bodies, non-governmental institutions, and private companies, SMEs, and you can see clearly from the beginning, also from the consortium, what is the orientation and direction of this project and the future competence center, meaning that we want to establish and tighten the links and the interaction and the relationships between various stakeholders, various institutions, various types of bodies that deal with the cultural heritage, primarily linking between research, academy, and the private sector, where the public bodies provide the support, the policies, and define the strategies for work. From the distribution map of countries, you see that we have a nice coverage of West and South Mediterranean countries, with representations also from the Balkans. The mission of this competence center for the future is to advise. So we should provide advice in what? In establishing a regularly updated map of research and cutting-edge technologies related to the preservation, conservation, and sustainable promotion of monuments and sites. We have to report on the most valuable initiatives, experiences, and best practices across Europe and internationally. Then the competence center should provide the support in order to promote a holistic and multidisciplinary approach to the conservation of cultural heritage, facilitate coordination between heritage agencies and cultural heritage institutions across Europe, and ongoing EU initiatives. So we have to really link with as many as possible EU-funded initiatives. Okay, build an effective partnership to promote the conservation and valorization of cultural heritage. So this is the cross-sectorial partnership that I mentioned. Enable the take-up and transfer of research project results by the cultural heritage sector. So here the public bodies have a fundamental role. And next, the competence center should provide services in defining training and upskilling programs for cultural heritage institutions, operators, and professionals. So probably most of you heard about the concept of the digital transformation, and we want to apply that as well here. We would like to develop consultancy, guidelines, and protocols. So this is a very important issue. concerning the use of ICT with a special attention to technologies for cultural heritage management. Who are we targeting? We are targeting public and private institutions responsible for managing European monuments, buildings, and sites, preserving them from damage and making them accessible for public enjoyment. We are also targeting cultural heritage professionals and private companies, providing services for preservation, conservation, and restoration, including large-scale and high-quality heritage digitization, and exploiting data to plan and manage interventions. Then we look at professionals and companies from the creative industry and hospitality sectors, which reuse data to produce heritage-based content, apps, games, education, and tourist services. And finally, and very importantly, heritage agencies, public bodies, such as ministries and decision makers, such as insurance companies, large owners, and so forth, who inform policies and strategies for conservation, preservation, and digitization. In the following slide, I will present a summary of the objectives of this project. So the first one is, as the title also says, to establish the methodological framework for the competence center, focusing on advanced digitization for the preservation, conservation of monuments and sites. So how we do that? We want to understand and map the risks for disaster prevention and mitigation, then collect successful research projects because we want to build on something that exists and see what's out there in terms of cutting edge technology. So for example, your conference is very, it's very timely in this, from this perspective. Identify user needs in the cultural heritage and related industries. And based on all these, we need also to create a strategic advisory board for the project validation. So somebody should tell us if we're doing it right or wrong. The second objective is to create a platform which we call knowledge base, which will have a lot of aggregations of technologies, of knowledge, of data. And you see here, for example, which kind of data we are talking. These are just some examples of big data services for accessing meteorological alerts about weather hazards. For example, then they should be linked within a HPC infrastructure for managing such data. The knowledge base of the project should include 3D semantic technologies, but not only, others as well, related to conservation, preservation, and valorization of monuments and sites. Tools for exploiting such digital assets, such as storytellings, apps, and so forth. Then all these data should be made accessible to a kind of cloud services that we look at how to develop it the best. Then objective 3 regards how to enhance and push forward the digitization of cultural heritage, keeping in mind conservation and restoration issues as well. Then provide training, support innovations and relationships with creative industries. And objective 4 deals with developing best practices. So we want also to say what we found useful for others to use as well. Develop this concept that probably you have heard of digital heritage twin, which should be based on various platforms, and the entire concept should be validated through pilot cases that we have foreseen in the project. Finally, the objective number 5 deals with setting up in terms of operational aspects, legal aspect, financial aspects, these competence centers. So we have to look at the structure, the support structure, the community engagement, and to find a sustainable funding model for the competence centers. what are these competence centers? I would like to, I hope it will work. Okay. Let me know if you hear it or if there is any problem.
4CH, Competence Center for the Conservation of Cultural Heritage. What are the aims of the project? 4CH aims to define operational, financial, and legal conditions to create a competence center focused on the preservation and conservation of historical monuments and sites. What is a competence center? The term competence center is used in different contexts to describe an infrastructure dedicated to knowledge organization and transfer. It is usually associated with excellence, training and knowledge transfer, interdisciplinarity, standardization, and a collaborative approach of different institutions or departments. 4CH. Follow 4CH on the website www.4ch-project.eu or on social networks.
Okay. And just to highlight a bit more, maybe political is not a nice word, but the importance of this project at a broader European scale, I brought to you another very short video, which it's here. So you see, it was a speech made by the Ambassador Michele Quaroni, for Deputy Permanent Representative of Italy to the EU. During the public session of the EU Council on...
Ricordiamo che l'Unione Europea attualmente finanzia, a valere sul programma Horizon 2020, un progetto finalizzato a istituire il quadro metodologico, procedurale e organizzativo di un centro di competenza europeo sul patrimonio culturale, in grado di lavorare senza soluzione di continuità con una rete di istituzioni culturali nazionali, regionali e locali, fornendo loro consulenza, supporto e servizi incentrati sulla conservazione dei monumenti storici e siti. La fitta rete e il quadro metodologico creati da tale progetto potrebbero costituire la base di un organo consultivo strategico che sviluppi, in ottemperanza al principio di sussidiarietà, una visione a lungo termine e degli strumenti utili alla promozione, salvaguardia e tutela del patrimonio culturale europeo. Grazie.
Okay, so I think by now it's quite clear what we want to do. You see here a conceptual drawing of how the competence center should look like, and how it should structure, and who would be in the executive committees, and how we are thinking at this stage at a very broad level, the link between national coordinators, regional coordinators, and at the European level. So the project itself and the competence center in the future is based on these three pillars of conservation, preservation, and valorization, whereas the foundation of all these is, of course, the interpretation, namely the research on cultural heritage. So I wanted to give you a small snapshot and insight of a very specific task within this broad project related to map of risks which can damage cultural heritage assets. Okay, in order to understand prioritizations of preservation and conservation activities, but also to try to understand which are the best or the most suitable approaches to document this kind of risk, damages, and how to create resilience of these assets. So this is a typical image regarding the resilience and built heritage, but not only built heritage, where we have a capacity building that we have to set up, pre-impact, emergency restoration, reconstruction, where We have to think in terms of preparedness, response, mitigation, and recovery. All these done through various primarily 3D digital technologies. So one of the first things that we have to define very clearly is what are we talking about when we mention the term cultural heritage. And actually it is a very, very difficult task. There are plenty of, not plenty, there are a few definitions. For example, ICOMOS provides definitions, but they are very specific to one or two of these pillars that I mentioned, not the three of them. So when we talk about cultural heritage, we have to think in terms of integration of the materiality. We have to consider the materiality of these assets, the environmental conditions, natural and human, and then try to link between causes and effects, particularly when there are multiple causes, multiple effects. You can think about the implications of this kind of analysis. So what you see here on in the blue shades is a preliminary idea of what we have to think in terms of monuments and sites in order to be able to further on, later on, document risk, assess risk, and so forth. So first of all, we have to understand what are we talking about in terms of cultural heritage. Is it a built one, a carved, or a natural? Then, under which, what is the status of investigation? It was studied in the past, it was just recorded and undocumented. We have some prior knowledge about it, and where is this knowledge? Any kind of interventions were done or not, and so forth. Then the location is very important. We have to understand the environment. Is this on ground, underwater, underground, or cave? Each one has its own peculiarities. Then, of course, the context is important. Is it in an urban environment with all the other factors playing a role, or it's in a rural environment, or even within a certain landscape? Very often, when we look at the monument, we have to think also about the biodiversity around that monument. Very often, monuments are situated within a very specific environment that has to be protected as well, in terms of fauna, flora, or the geology itself. Then we have to think of the function, what function it had in the past and what function it has in the present. Think, for example, various Roman theaters which are still used today, or things of churches that do not function anymore as churches, and they are now maybe conference meeting centers, and so forth. Then the structure is important. What is the composition? Is it a standalone building, or it's part of a complex or a larger ensemble? Last is the immaterial aspect of a monument. Monuments were made by humans for a certain, and they fulfilled a certain role, a social role. How do we capture this role? How do we keep in mind when we try to do conservation, these kind of roles? Think in terms of preservation of a theater, okay, if we're in the theater examples. When we do the conservation, we have to keep in mind to preserve as much as possible the ancient acoustics, if we know that in that place there were performances. So this is just one example. The same we do for artifacts, and you see here a detail of what is important to document and to consider when we look at artifacts. And the next stage regards understanding what kind of risks there are out there. So the first separation is between natural risks and human-inflicted risks. When we talk about natural risks, we have environmental ones, such as, and these are cumulative processes, for example, glaciation, erosion, silting, desertification, and so forth. We have also biological processes, for example, invasion of new species, animal migrations that move, vegetation that develops, and so forth. But we also have disasters, which are strong and short-term events. For example, severe weather, invasive species that just come in once, or large-scale geological events. In terms of anthropic risks, which are human-inflicted, again, here we may have two kinds: intended, so there was really an intention to damage, or they are just indirect because of other activities. So in the intended, we have heritage crimes, such as illegal excavation, illicit trafficking, theft, arson, vandalism, but very often we also have intended damages caused by management, modern reuse without thinking about past uses, corruption, political issues, political agendas, or sometimes even quarrying from ancient sites. And then we have
more.
Sorry?
You have 5 minutes more.
Okay, thank you. So, so you see here now what we want to do. We want to fill this matrix. So we have these definitions of risks, sites, and we have examples of damages. So we need to find what are the best technologies in order to capture properly, document properly, and then also assess the depth of this damage and propose various solutions to mitigate. So these are just some examples where, when we think about the monument, we have to think about many, many aspects within these monuments when we do the conservation, when we do the restoration, when we do the documentation itself. So we look at the material, the monument, the objects, and so forth. We cannot just separate one from the other. This is an example of a work in a World Heritage Site in Cyprus. These are the Tomb of the Kings, underground structures, where in blue here, this is a work that was done something like 10 years ago, and we mapped cracks. Now we need to understand why these cracks appear, and there are all kinds of reasons why. Okay, I will skip this example. There are some very good work done by ICOMOS, but this example that I brought here talks primarily about stones, but there are also many, many others. So I just brought it here so you know that this exists. And now what we have to do is take this and see which are the technologies that are most fitted to that. In order to achieve what we want to do, we have to think in terms of data, of course, because data is quite a lot in many, many domains. So we have to think in terms of data quality. And in order to assess data quality, we need to talk about data provenance, how we document that. Then, if we want to talk about interoperability between various systems, we have to talk about standards of data. So we have to think which kind of standards exist there. Ontology, is there an ontology regarding risk management or not? And vocabularies. And then, of course, sharing knowledge. So to sum up, this is what the Competence Center will do: promote a holistic and multidisciplinary approach to the conservation of cultural heritage and facilitate coordination between cultural heritage institutions across Europe. Services and tools to enable preservation and conservation using the latest, most effective technologies will be provided by establishing a map of research and cutting-edge technologies. This is what I started to show you above. By the way, the work just started in the project, so we have still more than 2.5 years. Report on the most valuable initiatives, define training and upskilling programs, and develop a consultancy regarding all these mentioned above. So thank you very much. I'm done.
Thank you very much for staying in time. And there is any question, curiosity, comments from the audience? I wonder, okay. Date voi la parola anche, Okay. So, please, Michela.
Ciao, Sorin. Nice to see you there. I have one little question related to the correlation or integration with ongoing initiatives such as ERIS. If there is a link, and how do you plan to build it?
Okay, so ERIS now submitted some documents to the to ESFRI in order to see at which stage we are in terms of development. Of course, there are many points of synergy that can happen, for example, through DigiLab, through sharing data. But primarily, if you think about the essence of these initiatives, IRIS is concerned mostly with linking and connecting laboratories. The Competence Center aims at something slightly different because they want also to strengthen the relationship between the public sector, the private sector, and research. So it's about setting up methods of collaboration, methods of dialogue. So they are in a way complementary. They're definitely not competitive. And I see that, I foresee, let's say, that in the future there will be a lot of dialogue between the two initiatives, particularly in terms of data sharing and feeding into each other several data. So bottom line, the Competence Center has a very, very specific role. Liaise between research, policymakers, strategies for development, and engagement of the public, of the private sector. IRIS, as I see, primarily aims at linking better the work of various laboratories. So I hope I answered.
Thank you. Any other comment? Sorry, Michela, you want to add more?
Just thinking, sorry.
Sorry, Michela. If there is any other point, I'm just asking you the way in which you gather the other information, because, for example, there are some technical committee about normatives that are widely used and so on. So how are you getting all the information apart from the different role of the different initiatives? But there is a lot of overlapping in all this work. I mean, you are using some methods, some tools in order to be more effective in connecting the many initiatives and schemes and knowledge that you, it seems that you are making some taxonomy, let me say in this way, maybe not. So there is some method that you are using in order to connect the different information and not to miss the relevant one.
Okay, so yes, you're totally right, because there are a lot of initiatives, there are a lot of bodies that deal with that, and one of the reasons why I'm here also today is to let you know about this initiative. So please, if you're interested to collaborate, contact me, Francesco, Franco, whoever, it doesn't really matter. We are looking, for example, systematically at the European Commission's website, monitoring EU-funded projects to record this. This is one way to find out what's going on at European level. We do the same way as much as possible through national initiatives in each of the participating countries. We are also monitoring various other programs within Horizon, such as Interreg, JPI, and so forth. within the advisory board of the competence of the project, there are institutions that should be able to tell us what's going on in these, in their own countries, such as relevant ministries. But of course, we may miss somebody, and that's why we try to advertise as much as possible the project. So these people that we may miss can contact us and should contact us directly.
Thank you very much for your presentation. And now I think that we can go on with the other one. We are ready. Violette Abergel. And I don't see her on the...
Yeah, she's there.
Okay, okay. Good morning. And, okay, so you can share your presentation, which is, I think, quite interesting, which is from data to the multidisciplinary knowledge, digital analysis approaches for cultural heritage preservation. So please, I remember to you also that you have 35 minutes for your presentation. Thank you.
Can you see my screen?
Yeah. Yeah.
Okay, good. So, hello everybody. My name is Violette Abergel, and first of all, I would like to thank Gabriela and all the organizers for this event and this kind invitation. I'm a postdoctoral fellow at the MAP laboratory in Marseille for more than a year, and I'm currently working on the visualization of spatiotemporal data in the context of the scientific project for the restoration of Notre-Dame de Paris. Okay, so very quickly, the MAP is a French research laboratory attached to the CNRS and the Ministry of Culture. It brings together 5 teams from Paris, Nancy, Lyon, and Marseille. And our works are particularly interested in architecture and mainly focus on 2 axes. First, model, method, and tools for architectural and cultural heritage analysis. And secondly, models and digital environments for architectural conception and design. So obviously, today I will focus on the first one. Of course, it's quite a wide research axis, which actually encompasses many issues related, among others, to digital data acquisition materials and protocols, to the optimization and automation of processing, archiving, disseminating, and so on. So we explored these topics through various projects for more than 20 years, and you can see here a few examples of past works. So today I'm not going to talk so much about mathematical models. I have no equation in my presentation, even if they are quite everywhere in our analysis approaches. I will more try to bring a global picture of the challenges related to the constitution of a multidimensional data corpus within multidisciplinary teams and of the perspectives that it could bring for us. So, if we look at the questions linked to heritage survey, we can see that these last decades, I've made method greatly evolve to the point of a radical paradigm shift. This diagram here represents, let's say, a classical survey process, which includes 3 main parts: description, figuration, and representation, which are all deeply interrelated. So basically, the work is done in situ, in front of the real object, and all the choices made in terms of measurement are closely linked to the choices made in terms of interpretation and representation, to the way we plan to hierarchize the information and so on. But with technological advances and with our new ability to easily and very quickly produce large amounts of digital data, this work is becoming more and more distant from the site. So now it's more like a sequential processing chain whose results are mainly based on a work of sorting, linking, or extracting information from digital data. And if this data, especially 3D, but not only, bring amazing opportunities for the study of cultural heritage, we can still note that this shift from on-site to remote raises new methodological issues. So in addition to a very strong risk of data dispersion, how can we include these new digital resources in a logic of knowledge production? Does more content always result in a greater understanding? And how can we correlate these new contents and for what expected services? So I think that regarding this context, the work done on the scientific worksite of Notre Dame is quite emblematic of some challenges that can arise in terms of data collection, processing, and analysis, especially in multidisciplinary contexts. So I will not speak so much about the context because I think you are already aware, but quickly, after the fires that hit Notre Dame almost 2 years ago, the CNRS and the Ministry of Culture set up a scientific project to coordinate all the scientific actions around the cathedral. So it's a very large research topic, and the project has two aims. Of course, to provide useful information for the restoration work itself, but also to benefit from a quite unique opportunity to renew our knowledge of the building, of its architecture, its history, its environment, and so on. So this project brings together nearly 200 people from more than 50 laboratories, which are divided into 9 thematic groups. And as you may have guessed, the work I'm going to present here is part of the Digital Data Working Group, coordinated by Livio De Luca, and which brings together about 30 people from 12 research units and 2 consortia. So this working group has many activities, but they mainly converge towards a common goal, which is to propose a digital ecosystem allowing to document in space and time the restoration site. So this ecosystem called the NDAM should be able to serve as a kind of digital memory, not only of the cathedral, but also of all the related research and restoration activities. So in practical terms, this ambition raises 3 major challenges. Firstly, at the level of data production and collection, which requires the implementation of methods and tools to aggregate within a single environment highly heterogeneous data produced by the numerous actors of the project. Another challenge is the enrichment of digital data through the implementation of methods dedicated to documentary and semantic characterization. The idea is to enrich this data with multi-thematic expert observations. And finally, a challenge concerning analysis and correlation through the construction, autonomous or not, of interconnections between the data collected according to criteria that can mix quantitative and qualitative attributes to facilitate their interrogation and understanding. So here you have an interesting example of this need to propose custom methods. As you know, during the fire, the roof structure burned and many remains fell on the walls. So to assist the sorting and to keep track of the position of these elements before their removal, the working group was asked to digitize it in 3D. But the place is really tight and only accessible to climbers. So the particular configuration of the site made it really difficult to use laser scanners and did not allow at all the use of drones as we do usually. So to solve this problem, Renato Saleri proposed to design a custom-made device to perform some photogrammetric acquisition. Actually, it's a kind of a cable cam, that's to say a mount with 3 cameras fixed on a device, which slides along a cable stretched across the nave. And with an upstream simulation, he can optimize the positioning of the cables and all the camera's parameters to ensure a sufficient coverage while optimizing the deployment time, which obviously had to have as little impact as possible on the worksite activities. So on this video, you can see the very first prototype, which at the time had only 2 cameras. It was later improved to make the acquisition even faster. And here you can see a resulting 3D point cloud. As you can see, it's quite dense with a resolution, I think, around 1 millimeter. Another example showing the importance of data collection is the work done by Kevin Jacot, who focused on the geometric restitution of the roof structure before the fire. In fact, even if laser scanning were done a few times before the fire, the 3D data concerning the roof structure is absolutely not exhaustive, mainly because of the complexity of the object. It's not really a coincidence we called it the forest. So given this very heterogeneous and fragmentary and even sometimes discordant documentary resources, Kevin had to rely on architects' drawings, but also on several thousands of pictures from various sources, and of course, the laser point clouds, incomplete but still rich in information. And from the analysis of all this data, he was able to propose a global manual modeling of the whole structure before the fire at the scale of the architectural detail. I think that this meticulous work shows the need to simplify the data mining operations, and it's definitely the idea that motivated the implementation of a collection method to centralize all the data in a unique environment. But centralizing data is not enough. An important part of the work is based on the enrichment through documentary and semantic characterization tools. So at this point, we have collected data, several hundred of 3D models of point clouds, thousands of images. But now, how can we ease their exploitation? So to do that, first of all, we must allow people to easily find resources that match their interests. So we have to document this data. That's to say, we have to describe not only the files themselves, their nature, their origin, their precision, and so on, but to describe also the information they contain, all the concepts they support. And of course, it's fundamental that this description work be based on stable vocabulary elements that reach consensus among the different communities involved in the project that often speak different languages. The role of OpenTESO is precisely to allow the structuring of multidisciplinary theory by defining concepts and the relationships that link them together, which can then be used to drive indexation and facilitate the search for information by harmonizing the description of the collective data. So now that we are able to collect data and that we have a vocabulary to support the descriptions, we can focus on their enrichment. The NDAM platform includes two tools for this. Firstly, a tool called ArcheoGrid, which allows us to index the data by relying on these thesaurus terms and on description models such as the Blinker, but also on more specific models defined by each working groups. Here again, I'll pass quickly, but there are videos to deepen this topic on our website. I'll show you the link at the end of the presentation. And then there is another tool called IOLI, which is quite complementary. It's dedicated to collaborative semantic annotation for the documentation of heritage objects. So the principle is based on the spatialization of images by photogrammetry. Basically, a user creates a project from a simple set of pictures of his study object, and these pictures are used to build the point cloud of the object. From this moment, the user can annotate any image of the project by drawing region on it, and this annotation will be automatically reprojected on the point cloud, but also on all the other images on which the same area is visible. The description structure of the annotations are freely defined by the users, so they can be based on thesaurus, text, dates, numbers, or any other attribute fields. And they can also contain complementary multimedia file like images, videos, audio comment, or whatever. So the practical application of this tool, in the case of Notre Dame, IOLI has been used to carry out projects following the diagnosis made by the architects in charge of the restoration. It's what you can see here in this video. So basically, each picture will be enriched with spatially defined observations whose description concern the alterations observed on the cathedral, the stone element to be replaced, and so on. So if we use all these tools together, we reach a point where we are able to collect data, all the data produced along the restoration sites, to describe them and to enrich them. That's to say, we are able to create a significant corpus of resources related to the very same cultural heritage object, in our case, Notre Dame. As you can see, these resources are still very heterogeneous. They concern various temporal states of the cathedral, various areas of interest. They are also of very different natures. Among them, we can find laser grammetric or photogrammetric 3D point clouds, pictures, drawings, but also restitution hypotheses, 3D meshes, semantic annotations, chemical analysis, and even spatialized sound samples. So finally, this context raises important issues in terms of exploration and manipulation, since in view of this diversity, the manipulation of each data would theoretically require the use of several specific software, which would obviously be a big problem in terms of accessibility. And also it would considerably reduce our capacity to cross the views between actors, whereas this project is deeply multidisciplinary. So to address this issue, we developed a 3D web viewer based on Pottery.js library. It's accessible from a simple browser to all the project members. And the aim of the viewer is to centralize and spatialize in a common reference system all the data related to the cathedral, whether they were produced before or after the fire. So the keyword is really to make easier the access to the data and knowledge produced all along the restoration. But this aggregation of resources must also facilitate the cross-visualization of the elements produced by all the working groups to help to identify potential correlations between different analyses, between different observations, and so on. So to do that, the very first step is to align each data with a reference model, or in other words, to calculate its position and orientation in a predefined coordinate system. So this operation is performed upstream before the web visualization. But in any case, once the spatialization parameters are known, the data can be loaded into the viewer, and it's done while maintaining a permanent link with ArcheoGrid. So in this way, each element is always linked to its metadata, and thus also to the vocabulary terms, which facilitates the exploitation and ensure their traceability. And of course, each element can be displayed and hidden freely by users. But to simplify the navigation, the cathedral space has been segmented into different volumes. These volumes follow the nomenclature of space in use for the restoration, which is predefined in OpenTeso. For example, a user can choose to display only the element concerning the choir, or more specifically, the tribunes of the apse, or even more specifically, the tier 1 span. So in this way, we can offer a first filter driven by users' interest. But here, it's only a filter by spatial proximity, but the very same logic could be applied to the metadata to build this time a filter by documentary or even semantic proximity. For example, if we want to display only the element produced by a specific person or at a specific time or representing a specific phenomena. And the viewer is also, is also connected to IOLI, the module dedicated to semantic annotation. So as I mentioned, in the case of Notre Dame, several projects were carried out on IOLI following the diagnosis made by the architects in charge of the restoration. Well, all these projects can be loaded directly into the 3D viewer, which is particularly interesting to contextualize and confront some observations made by the actors of the scientific project and the one made by the actors of the construction sites, and also to track phenomena on different temporal states before and after fire. The descriptive sheets associated with the annotations are also loaded as metadata. So as I said before, one of our targets would be to improve the exploitation of this information to filter the element visualized in 3D. For example, to display quickly all the stones that need to be replaced. Well, I won't spend much time on the interaction tools. They are quite classical. The large majority comes from the native functionalities of Pottery. In fact, for the interactions, the challenge mainly consists in proposing some ready-made parameters to facilitate the analysis in very specific contexts. However, it's obvious that the needs of the restoration site evolve over time, so we make the viewer evolve accordingly. For example, what you see here is the beginning of a work done with the metal working group on the loading of chemical analysis. They provide us with an Excel file containing different samples they analyzed. Each one is located in 3D by a simple triplet of coordinates and associated with a list of quantitative values characterizing its chemical composition. So these measurements are loaded into the viewer as shapes in the 3D scene, and the corresponding data are represented in the side panel as a diagram for better understanding. But in addition to the fact of just locating them in space, the interest of loading this kind of data in the viewer would be especially to allow to filter the display of the samples with thresholds. For example, to display in 3D only the samples whose lead content is higher than a given value in a specific area of the cathedral. And another example, what you can see here is a work done with the stone working group, whose goal was to realize the anastylosis of the collapsed vaulting ribs in the nave. So in red, it's the theoretical parametric model of the vaulting rib made using pre-fire data. And in the same time, all the arc stones found in the nave after the fire have been digitized in 3D. So from there, we are able to test different localization hypotheses by placing in one click each arc stone on a theoretical position. And we have also, so here, I place a stone on its theoretical position. Yeah. And also we have the possibility to quickly invert the backside and the front side of the block, to change its color, to show the uncertainty of the hypothesis and so on. And of course, it's also possible to export a synthesis table of the hypothesis, and the same approach could be applied to many other study cases on the site. For example, rough structure remains. And to finish with this example, I think the arc stones are a really interesting case study in terms of visualization and manipulation, because we know for part of them their post-fire position, and we have some hypotheses of pre-fire positioning. So finally, each block is associated with several spatialization information. So in this case, which one do we use? So to answer to this kind of situation, we set up a kind of temporal slider, which allow to change the position of a block in the course of time. So here you can see the N1A stone, which returns back to its pre-fire position. So we are virtually moving up the arc. Obviously, it raises a few problems first, because we have to interpolate the known positions to deduce a trajectory, which does not correspond to any physical reality. On this video, you can see that the block crosses the wall. And also because it raises important matters in terms of temporal granularity, since in order to go further, we would have to be able to characterize the chronology and the scale between different ways of expressing a date, a moment, a time. And I will finish on correlation. I think that today this work opens very interesting perspectives in terms of analysis, since the corpus we managed to create will allow us to introduce new data multidimensional correlation mechanisms, taking into consideration at the same time the notions of space, of shape, of time, and of knowledge domain. So the idea would be to set up mechanisms, autonomous or not, but able to propagate some semantic attributes to all the relevant resources from the corpus, thanks to the information accumulated during the documentary and semantic categorization stages, and also to build new interconnections between the resources and between the concepts manipulated. This new interconnection can be based on the cross-analysis of all the corpus elements. So in other words, the idea is to try to characterize some links between actors some links between disciplines mobilized on the project, some links between the observed phenomena to detect possible occurrences, synonyms, and why not even causal relationships. So the goal would be to be able to provide exploration and interrogation tools capable of taking advantage of all the quantitative and qualitative information accumulated within the very same environment. So on this point, there are many interesting things to explore. For example, to enable some multi-criteria queries, such as I wish to visualize in 3D any resource representing a vestige whose length is greater than 1 meter found in spaces bordering the T22 span and prior to the June excavation. Of course, this example is purely fictive. It was just to give an idea, but it's clear that it's quite complex in that it includes several criteria of very different natures. First, we have a documentary criterion with any resource, which gives us an indication of the file types expected in output, here any types. Then semantic, since the extracted resources must be linked in one way to another or another to the term vestige, which implies being able to define precisely what this concept refers to and which concepts are close or similar to it. Then a geometric criterion, which gives us limits on the dimensions of the projection of the vestige in the 3D reference system, which necessarily implies being able to set a link between a semantic assignment and a geometry. Also, a special criterion with a precision on the relevant span, which implies being able to define precisely the nomenclature for space and shapes and the hierarchical relations between the elements resulting from this division, but also to control the spatial referencing of all the corpus elements. And finally, a temporal criterion, which requires several things. First, to be able to date all the resources, which raises questions of granularity, and also to do it in an harmonized way, thus relying on the shared and stable temporal division, and it's really not trivial. So I do not have much time left, so I will finish there. But basically, our idea would be to rely on a kind of meta-knowledge model built as a big graph, synthesizing all the information related to the project, whether in terms of spaces, shapes, actors, and so on. So this graph will have to be continually updated through correlation mechanisms that will constantly seek to define new relationships between nodes. And then the joint exploitation of this graph and the capacities of 3D rendering engines in terms of geometrical analysis should allow us to execute quite fine queries on the corpus from both quantitative and qualitative criteria, and eventually to arrange informational spaces to propose new exploration modalities, for example, which can be based on intuitive expression modalities like natural language or serendipity. Well, it's a work in progress, which is very exploratory for now. We started to have interesting results, but there is still a lot of stuff to do. But I really think that it could open up very interesting perspectives, not only for the continuation of the project, but also to better understand the mechanisms that lead from data to knowledge into different communities around the same cultural heritage object. Well, I stop here. I hope I didn't take too much time. Thank you for your attention. And here, the link for our website.
Thank you for your very nice presentation. And for me, working with data, looking at this is really, really nice. So there is any question, comments, curiosity from the people that here, or maybe just from people which is online? A quick curiosity, because it seems really a huge system. You already started from some blocks and you put that together, because it seems really astonishing, the complexity of the system that you're using.
Yeah. In fact, at the beginning of the work, we have seen that some technological blocks can be used and merged together at the service of Notre Dame. So some elements like ArcheoGrid, OpenTeso, or IOLI already existed and was under development, but the event around Notre Dame kind of drive the further developments around all these technological bricks.
Thank you. Any other question? So we thank you again very much for your nice presentation.
Thank you.
Okay, so I think that we finished this morning.